Hello all and welcome to the section 5.2 lecture, video lecture on sigma notation and limits of finite sums. So what we're building towards here in chapter 5 is the idea of the definite integral and how that relates to areas under curves. And so in the last section we talked about how to approximate the area under the curve by making rectangles and then adding their areas together. So what we'd like to be able to do is we'd like to be able to use another notation to simplify that when we have a large number of rectangles. And then beyond that, we'd like to say, well, what if we had an infinite number of rectangles? So if we had an infinite number of rectangles, then each rectangle would have a width of 0. And so basically what we would do when we add those all together is we would get the area under the curve if we had a large number of rectangles, if we made them very small. And so that's what we're building towards. So in order to do that, the first thing we need to do is we need to be able to talk about summation notation, sigma notation. So the idea here is sigma notation enables us to write a sum with many terms in a compact form. So this big E looking thing is the Greek capital letter sigma. And in math, it stands for the sum of. And so what it's telling us to do is sum the first k equals 1 elements, the elements from k equals 1 up to n. So if we start a sub k, then we add a sub 1 plus a sub 2 all the way up to a sub n. So in an actual example, what this looks like is if I start at 1 and I go to 5 and I want to add k together, that means I want to add the first 5 elements together, where k is whatever element I'm on. So I would start with k equal to 1, so I would plug 1 in for k, so that would just be 1. Then if I plug the next number in, which would be 2, in for k, I get 2. If I plug the next number in for k, then I get 3, 4, and 5. Okay, so I get the first 5 elements where the number is, in this case, whatever we plugged in. And so in this case, I add those together and I get 15. Okay, similarly, the second one wants us to start at 4. So we are using k equals 4. And then we want to go to 5. So that we're starting at 4 and we're going to 5. So that means we're only going to have 2 things. And we want to plug those numbers into k squared over k minus 1. So that would be 4 squared over 4 minus 1 plus 5 squared over 5 minus 1. Okay. And then you can either use the calculator or do this by hand, but you need to simplify that. So one simple way to do this would just be to plug that into the calculator. So that would be 4 squared divided by 4 minus 1 plus 5 squared divided by 5 minus 1. And so in a fraction form, we get 139 over 12. Okay, and so that would be the answer there. The next one, same idea. I'm plugging 1 in for k, and I just want to add these all together. So I'm going to have 5 elements here because I'm going from 1 to 5. And I start with sine of 1 pi plus sine of 2 pi plus sine of 3 pi plus sine of 4 pi plus sine of 5 pi. And then we simplify each one of those. Once again, you could use the calculator if you want, but if I'm doing this one here, it's simple enough. Sine of 1 pi is 0, sine of 2 pi is 0, sine of 3 pi is 0, sine of 4 pi is 0, sine of 5 pi is 0. So I add those all together, and I get 0. Okay, so with the next one here, we're going for, why don't you all pause the video for a second, try these last two, and then when you replay, hit play on the video, we'll go through them together. Okay, so the first one here, I plug in 1 for k because I start at 1. And then I plug in 2 for k. And then I plug in 3 for k because I'm going up to 3. Okay, so that would be negative 1 times 1 plus negative 1 times negative 1 is positive 1. So positive 1 times 2 plus negative 1 times 3. So that'd be negative 1 plus 2 plus negative 3. Add those together, and you get negative 2. Okay, so one really important thing to notice here is I alternated signs. And the part of this problem that does that is the negative 1 to the power part. So when you are doing a problem and you want to alternate signs, this term, negative 1 to the k, is how you can do that factor. Okay, and then the last one, we're going to go from 1 to 2 of k over k plus 1. So we plug in 1, so that would be 1 over 1 plus 1 plus 2 over 2 plus 1. We're just replacing k with 1 and then with 2. So that would be 1/2 plus 1/3, which is 5/6. Okay. And so that's the idea of how sum notation works. Now we should also be able to work in the opposite direction. So if we flip to the next page, we can give that a try. So when you're working backwards with these, what you want to keep in mind is what k is. And remember, k always increases by 1, and unless we're told otherwise, it always starts at 1. So if we assume our k here, we have 4 terms, right? So that means we're going to have k 1, 2, 3, and 4. And what you want to ask, right, in our sum notation is going to be k equals 1 to 4, because we have 4 terms. What you want to ask yourself is, what am I doing to the numbers 1, 2, 3, and 4 to get 1, 4, 9, and 16? And the answer is you square them, right? This is 1 squared plus 2 squared plus 3 squared plus 4 squared. So in general, what we're doing is k squared. And there's our expression written in sum notation. Okay? And so there's the idea. So if you wanted to at this point, you could pause the video and try the other two. And then when you hit play, we'll go through them together. Okay? So then for both of these, we should notice that there are 5 terms. So we're going to look at k equals 1, 2, 3, 4, and 5. K equals 1, 2, 3, 4, and 5. And then for the first one, you ask yourself, and so our sum notation, for both of them would be k equals 1 to 5. Okay? And then you ask yourself, well, what do I have to do to 1, 2, 3, 4, and 5 to get 2, 4, 6, 8, and 10? And for the first one, the answer is multiply them by 2. Right? 2 times 1 is 2. 2 times 2 is 4. 2 times 3 is 6, and so on. And then for the second one down here, well, what do I have to do to 1, 2, 3, 4, and 5 to get negative 1/5, 2/5, negative 3/5, 4/5, and negative 1? Well, first you can notice that we're alternating in sign, so we're going to have the factor of negative 1 to the k involved, right? Because on the previous page we saw that if we had negative 1 to the k, that alternates the signs of the terms. And then I have to divide these by 5, right? 1 divided by 5 is 1/5, 2 divided by 5 is 2/5, 3 divided by 5 is 3/5, 4 divided by 5 is 4/5, and 5 divided by 5 is 1. So this would be k over 5. And that's the idea. Okay. Now, what we're building towards here is the idea of letting n go to infinity. So finding the limit of these finite sums is we let n get really, really big. So if we're going to do that, we're going to need some rules where we don't have to write out all the terms, because if you have to write out all the terms and there's an infinite number of terms, you'd never get done with a problem. So on the next page, we have some rules. So the first rule is that if you have a sum within a summation, you can break it apart into 2 summations. The same goes for subtraction. Another really important rule is if you have a constant times an expression inside a summation, you can bring the constant out in front, right? That's what they're doing here. They're bringing the constant out in front so that you're doing the summation first and then multiplying by c. The next one is if you want to find the sum of a number over and over again. So like, for example, if I wanted to do the sum of k equals 1 to 10 of 12, well, what you do is you simply multiply however many terms there are times the number, right? If I want to add 10 12s together, that's the same thing as multiplying 10 times 12, which is 120. And so that's what they're looking at here. Is if you have a constant inside your summation and that's it, you can just multiply the constant times the number of terms. And then the last 3 here are very important. They are the ones that allow us to take these sums and do what we're going to do. So if you wanted to do one of the problems we already did, the first k terms, you just take n times n plus 1 over 2. If you want to do the first n squares, you do n times n plus 1 times 2n plus 1 over 6. And if you wanted to do the first n cubes, you do n times n plus 1 over 2 squared. And for now, these are what we're going to use, right? So here in what we're going to do on this page, these are the expressions we're going to use. But later on, we're going to want to have these as, to save ourselves some time, we're going to want these multiplied out. So another way to write n times n plus 1 over 2 is as n squared plus n over 2. Another way to write the second one here, I can multiply the first two factors together. So that's n squared plus n times 2n plus 1 over 6. So we multiply that out and we get 2n cubed plus 3n squared plus n over 6. And then for the last one, we multiply inside the parentheses and we get n squared plus n over 2. And then we can square that and get n to the fourth plus 2n cubed plus n squared over 4. And so for now, we're going to use the typed ones here, but later on, we're going to want to use these multiplied out versions for what we're going to be doing later. So that's just to save us a little time later on. So the idea behind these rules is to use the first three rules to write our summation in one of the last four forms. So in this first one, the first thing I want to do is get rid of those parentheses, because nowhere up here does it talk about multiplying a variable times a variable. So if I get rid of the parentheses, I get the sum of k equals 1 to 7 of 2k squared plus k. Then I can use the constant multiple rule and the summation rule to break apart this sum inside and move the 2 out in front of its summation. So that would look like this. 2 times the sum from k equals 1 to 7 of k squared plus the sum from k equals 1 to 7 of k. Okay, and the reason I did that is because now I can use these rules for the first n terms and the first n squared terms. So this first one will become 2 times the first k squared terms. So it's n times n plus 1 times 2n plus 1 over 6. In this case, n is 7. So it would be 7 times 7 plus 1 times 2 times 7 plus 1 over 6 plus the first 7k terms. So n is still 7. So this would be 7 times 7 plus 1 over 2. And now either by hand or using a calculator, you can figure out what that is. So if we use the calculator, it would be 2 times 2 times 7 times 7 plus 1 times 2 times 7 plus 1 all over 6 plus 7 times 7 plus 1 over 2. When we do that, we get 308. Okay, so that's what we're looking for. Now, for the next one, there's one more rule we need. Notice that all of the problems up here, k starts out as 1, right, if I look at all of them. So what I need is well, how can I rewrite this sum with using k equal 1 problems? Well, the nice thing about this is the sum from k equals m of a sub k to n is equal to the sum of k equals 1 to n of a sub k minus the sum from k equals 1 to m minus 1 of a sub k. So the idea here is if I want to do the sum like this problem down here from 3 to 17, well, I just find the sum from 1 to 17 and I subtract away 1 and 2. So like, for example, in this problem down here, it would be the sum from k equals 1 to 17 minus of k squared minus the sum from k equals 1 to 2 of k squared. And so notice what that will do is it will get rid of the 1 and 2 from the left-hand term using the right-hand term. And now we can use our rules. So this would be 17 times 17 plus 1 times 2 times 17 plus 1 over 6 minus 2 times 2 plus 1 times 2 times 2 plus 1 over 6. Okay, and so now we can put that into our calculator to simplify. So 17 times 17 plus 1 times 2 times 17 plus 1 all over 6 minus 2 times 2 plus 1 times 2 times 2 plus 1 over 6. When we do that, we get 1,780. Okay, and then the last one here is about, well, what can we do with n? What if we wanted to write this without knowing what our endpoint of our sum would be? Well, we can use all the same rules again. So we're going to multiply, rewrite this first using the difference rule. So that's k equals 1 to n of k minus k equals 1 to n of 1. And now we can use the rules at the top. So the rules for the first n k's, now this is where we're going to want to use the multiplied out version. So that's going to be n squared plus n over 2. And then the rule for minus a constant is simply n times the constant. So that would be minus n times 1. And now we can do some simplification if we want. So this would be n squared plus n over 2 minus 2n over 2. And then we can combine like terms to get, this would be n squared plus, minus n is what we would get for the sum there. Okay, so at this point, go ahead and flip over to the next page and hit pause and try doing these problems on your own. And then when you're ready, you can hit play again and we'll go through them together. Okay, so let's go ahead and go through these. So the first one is just using the k cubed rule. So this would be 10 times 10 plus 1 over 2 squared. So that's well, now just put that in the calculator is the quick way to do it. So 10 times 10 plus 1 over 2 squared. And so that's 3,025. Okay. The next one, we can bring the constant out in front. So this would be pi over 15 times the sum from k equals 1 to 5 of k. So that'll be pi over 15 times 5 times 5 plus 1 over 2. So that'll be 30 pi over 30, which just equals pi. The next one, start by using the difference rule. So this is the sum from k equals 1 to 6 of k squared minus the sum from k equals 1 to 6 of 5. So that would be the square rule, which is 6 times 6 plus 1 times 2 times 6 plus 1 over 6 minus 6 times 5. Okay, and for that one, we're going to get 61. And then for the last one, we need to use the last rule we talked about, which is this doesn't start at 1, so I need to fix that. So that'll be the sum from k equals 1 to 36 of k minus the sum from k equals 1 to 8 of k. And now we can use the rules for k. So this is 36 times 36 plus 1 over 2 minus 8 times 8 plus 1 over 2. And so that should be 630. Okay, so that's how our summation rules work. Now what we really want to be able to do with this is we want to be able to write expressions for things that look like this with an n, like n squared minus n over 2, and then we want to be able to find the limit as n goes to infinity. So that's what we're going to try and do here, to find areas under the curve. So if we look at the next page, this leads us into Riemann sums. So Riemann sums is the theory of limits of finite approximations, which was made precise by the German mathematician Bernhard Riemann. And so his idea was that if I take an interval x sub 0 to x sub n and I partition it into a bunch of subintervals, each of one looks like this, and in each interval we select some point that the point chosen in the kth interval is c sub k. On each interval, we stand a vertical rectangle that stretches from the x-axis to touch the curve at c sub k comma f of c sub k and has the width delta x sub k. So the area of the rectangle is f of c sub k times delta x sub k, and the sum of these areas is written like this. So if we were to look at a specific example here, let's just go ahead and do a couple of these examples using this one. So I'm just going to look at this one. So I went ahead and gave you the graphs for these. So if I were going to do left-hand endpoints notice that our Riemann sum has a 4. So we're going from 1 to 4. So that means we have 4 subintervals. So I'm going to break this into 4 equal pieces. Okay. And then the idea is to use the left-hand sum, the right-hand sum, or the middle. So if we use the left-hand sum first, that means I'm going to make rectangles by starting at the left-hand side of each subinterval. That's going to give me my height. So my rectangles would look like this. Okay? And then what we would simply do is we would take our f of x, which is these points, the y values for those points, times delta x. And delta x, as we kind of saw in the last section, that would be 0.25 in this case. Okay, and that's the idea. So you basically are summing things together, and what you do for each k value is you find the value of the endpoint in the function. We could also do this with right-hand intervals, in which case if I separate it into 4 subintervals, and I do the right-hand intervals, my rectangles would look like this if I'm using the right-hand side to determine how tall the rectangle is. And if we use either one of these and we let n keep getting bigger, so my rectangles keep getting smaller and smaller and smaller, then I'm going to get closer and closer to the actual area under the curve. And if we let n go to infinity, then we will actually find the area under the curve. And that's what we're going to end up talking about. But before we do that, there's one more term we need to mention, which is the idea of norm. So we define the norm of a partition P written with 2 absolute value bars on each side of P to be the largest of all the subinterval widths. So in this case, if my partitions are at -2, -1.6, and so on, my subintervals would be -2 to -1.6, -1.6 to -0.5, -0.5 to 0, 0 to 0.8, and 0.8 to 1. And so now the norm is whatever the largest of those is. So the first one, it would be 0.4 is the width of that subinterval. The width of the second one is 1.1. then 0.5, then 0.8, and then finally 0.2. So the largest one and our norm would be 1.1. So that's a term that will come up moving forward, but it's not that important, so we're not going to spend that much time on it. What we are going to spend a lot of time on for the rest of this section is talking about the idea of using Riemann sums and their limits to find the area under the curve. So it says for the functions below, find a formula for the Riemann sum obtained by dividing the interval a comma b into n equal subintervals and using the right-hand endpoint for each ck. Then take a limit on these sums as n goes to infinity. So let's talk about some generalities first of all. So if here's my subinterval from a to b, and here's my graph of my function. I don't really know what it looks like, but let's just say it looks something like that. And I draw rectangles on that using the right-hand endpoint, then they would all look like this. There's my first subinterval. Okay? And so the question becomes that we need in order to use the Riemann sum. Remember, Riemann sums are SB equals the sum from k equals 1 to n of f of ck times delta xk. So the key is we need to know what those are in general. So if we start with delta xk, and we look at this picture, well, each one of these subintervals is simply going to be the total width divided by the number of subintervals, right? If I have an interval that's 10 units across and I have 5 subintervals that are all equal, I can take 10 divided by 5 and get a width of 2 for each one of those. So we simply take the largest value minus the smallest value divided by the number of subintervals, and that will tell us the width. Then our CKs, each one of these right-hand endpoints is simply going to be A plus the width, right? We start at A plus the number of widths we're on. So the first subinterval, we would add 1 width, right? K would be 1. Then the second subinterval, we add 2. Then we would add, then we'd have to add 3, right? That's the third subinterval to get wherever this value is, right here. And that's the idea. So CK is going to be A plus K times B minus A over N. Okay, so in general, what you're going to be finding when you do these is S sub P equals the sum from K equals 1 to N of F of A plus K times B minus A over N times B minus A over N. Okay, so we're just going to be substituting into that general formula. So in this case, A is 0 and B is 1. So we can go ahead and substitute those. So S sub P would be the sum from K equals 1 to N of 0 plus K times 1 minus 0 over N. And then we have to substitute in for F. In this case, F of X is X squared. So this would be squared times 1 minus 0 over N. Okay, so we're just substituting into this formula our F, our A, and our B. And now we want to simplify. So S sub P equals the sum from K equals 1 to N of 0 plus nothing. That's going to go away. 1 minus 0 is 1. 1 times K is K. So this will be K over N squared times 1 minus 0 over N, which is 1 over N. And then if we multiply these together, we get K squared on top, because K squared times 1 is K squared. And on the bottom, we get N squared times N, which is N cubed. Okay. And now we can use our sum rules to get rid of the constant. So what's the constant here? Well, the constant is N, because N is fixed by whatever number's on top of our summation there. So I can bring the fraction 1 over N cubed out in front of my summation. So this would be SP equals 1 over N cubed of K squared. So from K equals 1 to N. And now we can use our K squared rule. So we can come up over here, and our sum, SP, will be 1 over n cubed times the sum of the first k squared elements, which is 2n cubed plus 3n squared plus n over 6. And then we can multiply those two together. So S of P equals 2n cubed plus 3n squared plus n over 6n cubed. Okay, so let's just review real quick what we've done so far. Because now we've got an equation for the sum. So we first plugged in A, B, A, and K, A, B, and F into this general formula we given right here, this general formula. We plugged those values in, then we simplified. Then we brought the constant out front, and then we were able to use our sum rule to get the sum of the first k squared elements. And so now we can find this limit. So we want to do the limit as n goes to infinity of this expression. And to do that, remember what we do is we divide this into individual pieces. So 2n cubed over 6n cubed plus 3n squared over 6n cubed plus n over 6n cubed, and simplify. So this would be the limit as n goes to infinity of 1/3 plus 1 over 2n plus 1 over 6n squared. And then as n goes to infinity, what we need to remember is that anything with an n in the denominator goes to 0. So these last two terms would both have a limit of 0, and the limit of a constant is simply that constant. So the limit of 1/3 is just 1/3. And there's our value. So the area under the curve for x squared over the interval 0 to 1 would be 1/3 units. And that's exactly what it is. Okay? And so that's the idea. So now let's try another more complicated one together. Okay, so we're going to do the same idea as the one we just did. It's just going to be a little more complicated because it's a more complicated function. Okay, so this one, we're going to do exactly the same thing we did up here. We're going to plug a plus k over b minus a in for n. What might be a useful thing to start out here would be, well, what is a plus k times b minus a over n for this function? So a is -1 and b is 0. So 0 minus -1 over n. And so that would be, that would simplify to -1 plus k over n. Okay, so now we can plug that into the function. So this will be S of p equals the sum from k equals 1 to n of the function of this value. So plug that in for x squared, for x and x in x squared and x cubed. So this would be -1 plus k over n squared minus -1 plus k over n cubed. And then once again, we're going to multiply that by b minus a, which was 1 over n. Okay, and so now we're just going to simplify like we did before. So we're going to multiply some stuff out, which is going to get a little complicated, but it's just algebra. So -1 times k over n squared is 1 minus 2 k over n plus k squared over n squared. And then the opposite of -1 plus k over n cubed is 1 +1 minus 3k over n plus 3k squared over n squared minus k cubed over n cubed times 1 over n. Okay, and then we can combine like terms. So that would be 1 plus 1 is 2. Negative 2k over n minus 3k over n is negative 5k over n. K squared over n squared plus 3k squared over n squared is 4k squared over n squared minus k cubed over n cubed times 1 over n. And now we can distribute the 1 over n. Or actually, the better thing to do here would be... No, I'm going to stick... Yeah, distribute the 1 over n. So this is the sum, k equals 1 to n, of 2 over n minus 5k over n squared plus 4k squared over n cubed minus k cubed over n to the 4th. Okay. And so now at this point, we're kind of running out of room here in our notes, so I'm going to go to a separate sheet of paper with this. So what I'm going to try and do... nope, that's not what I wanted to do. That's not working either. But anyway, so let's go ahead and go to our notes. And I'll write this out here separately and we'll keep going. So F over P equals the sum from k equals 1 to n of 2 over n minus, and let me just check what that was again, minus 5k over n squared so minus 5k over n squared plus 4k squared over n cubed plus, minus k cubed over n to the 4th. And so now we can use our sum rules to simplify this. So S sub P equals the sum from k equals 1 to n of 2 over n minus 5 over n squared times the sum of k equals 1 to n of k plus 4 over n cubed, the sum of k equals 1 to n of k squared minus 1 over n to the 4th times the sum of k equals 1 to n of k cubed. Remember, anything that's an n or anything that's not a k can come out front because it's a constant. Okay? And so now we use our rules. So this will be S sub P equals, here we just take n times the constant, so n times 2 over n. In the second one, it's 5 over n squared times the rule for the first k elements, which is n squared plus n over 2. For the next one, it's 4 over n cubed times the rule for n cubed k squared elements, which is 2n cubed plus 3n squared plus n over 6. And for the last one, it's negative 1 over n to the 4th times the rule for the first k cubed elements, which is n to the 4th plus 2n cubed plus n squared over 4. And so now we can multiply all this stuff out. So S sub P equals n's cancel. We just get 2 minus, so multiply this all together. So you get negative 5n squared over 2n squared minus 5n over 2n squared plus 8n cubed over 6n cubed plus 12n squared over 6n cubed plus 4n over 6n cubed minus n to the 4th over n to the 4, n to the 4th minus 2n cubed over 4n to the 4th minus n squared over 4n to the 4th. And so I know this is complicated, but we're just doing a lot of multiplication. So if you need to pause at any point and try this multiplication on your own, feel free to do that or look at the steps individually. And so now simplify each one of these. So here the n squares cancel, so that's 5 halves minus 5 over 2n plus 4 thirds, right? Because these cancel, n cubes cancel, and 8 divided by 6 is 4 thirds, plus 2 over n plus 2 over 3n squared minus 1/4, because the end of the fourths cancel, minus 1 over 2n minus 1 over 4n squared. And now we can take the limit of that as n approaches infinity. Or actually first, before we take the limit, let's combine like terms. So SP, so we've got a 2 negative 5 halves, a 4 thirds, and a negative 1/4. So put that, quickest way is probably to put that in our calculator just to be sure. So when I put that in my calculator, I get 7/12. And then we've got negative 5 over 2n, 2 over n, and negative 1 over 2n. So those are like terms, so you can add those together with ignoring the n's. So that'd be 5 divided by 2 plus 2 minus 1/2. And so that's 4. So, whoops, because I forgot a sign here. It's actually negative 1, sorry, so minus 1. And then we've got the n squareds. So we've got those two terms, so 2 thirds minus 1/4. And that's, so 1 over, sorry, not 1. 1 over n. And then this one is plus 5 over 12n squared. And now we can find the limit of that. So the limit as n approaches infinity of 7 over 12 minus 1 over n plus 5 over 12n squared. These two terms both approach 0 because they have an n in the denominator, so we just get 7/12. Okay, and so that's the idea. So that's a pretty complicated one. And the nice thing about these that we're working towards is once we get the idea of how these work, we're gonna learn some rules, and we'll be able to prove some rules that will make our lives a lot easier. So right now that's pretty complicated, but like I said, once we have some more better rules to do this, our life will get a lot easier. So this is the last page of this section, so why don't you all take a moment, pause the video, and try these two on your own, and then when you're done, we'll go through them together, and that'll be it for section 5.2. Okay, so now that you've all had a chance to try these two, let's go ahead and work through them together. So once again, we start out with S of P equals the sum from k equals 1 to n of f of a plus k times b minus a over n times b minus a over n, and we plug in our values for this. So in this case, r's are our f is going to be 2 times, so it's going to be 2 times whatever's inside. So our a is 0, k is the variable, our b is 3, our a is 0 over n, and then b minus a over n. Okay, and then we simplify. So this is S sub p equals the sum from k equals 1 to n of 2 times 0 goes away, 3 minus 0 is 3, multiply, and you get 3k over n times 3 over n. Multiply those all together. 2 times 3 is 18k over n squared. Bring the constant out in front, So S of p equals 18 over n squared times the sum of k equals 1 to n of k. And now we can use our rule. So let's come up here. So S of p equals 18 over n squared times n squared plus n over 2. Distribute, and you get S of p equals 18n squared over 2n squared plus 18n over 2n squared. Simplify, and that's S of p equals 9 plus 9 over n. Find the limit of that, and you just get 9. And this is a nice one to look at because we can show that that's the area of the curve because of what this graph looks like. So if I draw a quick sketch of this graph, what it would look like is we're going from 0 to 3, and it's a straight line that looks like this. So what it makes is a right triangle. And if you plug in 3, you get 6. So the base of this rectangle is 3, the height is 6, the area of a rectangle is 1/2 base times height. So this is 1/2 times 3 times 6, which is also 9. So this is a good one because we can verify what we've been doing with the summations and the limits here. Okay, and then the last one we can do together. It's similar to the second one we did together, except it's a little easier because a is 0. And anytime a is 0, that's going to make our life slightly easier. So like in this case, we're finding a plus k times b minus a over n. If we plug in those values here, it's going to be 0 plus k times 1 minus 0 over n, which is just going to be k over n. So our thing we're plugging into the function's a lot simpler here. So S sub p is going to be the sum from k equals 1 to n of k over n plugged into this function. So that would be 3 times k over n plus 2 times k over n squared times b minus a over n, which is 1 minus 0 over n. Okay, and so then we can simplify this out a little bit. So k equals 1 to n. So if I multiply inside, I get 3k over n plus 2k squared over n squared times 1 over n, and then I can distribute. So S sub p equals the sum from k equals 1 to n of 3k over n squared plus 2k squared over n cubed. Then break this sum up and bring out the constants. So this is S sub p equals 3 over n squared times the sum k equals 1 to n of k plus 2 over n cubed times the sum of k equals 1 to n of k squared. And so now we can use our sum rules. So this is S sub p equals 3 over n squared times the sum of the first k, which is n squared plus n over 2, plus 2n over n cubed times the sum of the first k squared, which is 2n cubed, plus 3n squared plus n over 6. Okay, and now we can multiply that out. I'll do the distribution. So S sub p equals 3n squared over 2n squared plus 3n over 2n squared plus 4n cubed over 6n cubed plus 6n squared over 6n cubed plus 2n over 6n cubed. And now that we've done that, we can simplify those. So S sub p equals the n squareds cancel, so 3/2 plus 3 over 2n plus 2/3 plus plus the 6's cancel and 2 of the n's cancel. So 1 over n plus 1 over 3n squared, and then combine like terms. So S sub p 3/2 plus 2/3 is 9/6 plus 4/6, so that's 13/6. 3 over 2n plus 1 over n is 3 over 2n plus 2 over 2n. So that's 5 over 2n plus 1 over 3n squared. And now find the limit of that. So the limit as n goes to infinity of 13 over 6 plus 5 over 2n plus 1 over 3n squared. Once again, these have an n in the denominator, so they go to 0. So that leaves us with 13/6. Okay, and that's the idea. And that's what we're leading towards. But like I said, as we get better at this, just like with derivatives, we're going to have an easier way to do this that doesn't involve limits once we know the method to proving those rules. So that's it for this section. Don't forget to do your homework and all the other assignments on my math lab. And if you have any questions, feel free to call, text, or email me. And check your email for upcoming office hours.